Welcome back. We've been talking about Markov chains and Markov models, and we introduced the definition of a discrete time, discrete space Markov chain. It satisfied this graphical model. And then I mentioned a few generalizations. You can have higher order Markov chains, and you can also have some other, you can introduce continuous time or continuous space Markov chains. And then I gave you an example of a discrete time, discrete space Markov chain. Discrete time and discrete space. And this was just a random walk on the integers. Random walk on z. And we increased with probability 1/2 and we decreased with probability 1/2. So this will be one sample, you know, and you could have another sample and so on. And let me give you now another example. So example 2. A simple example. So by the way, the set here that xt took values in, it was all of the integers, right? So it was infinite, but it was still a countable set. So this was a countable, or rather this was a discrete space thing. Another simple case would be if we wanted to model just a super oversimplification of the weather would be something like this. We could have the following states. We could have sunny, we could have rainy, we could have snowy, or we could have cloudy. Say there's only 4 in a super simple model of the weather. We just had these 4 possible states. And we could model the transition. Say the weather took exactly one of these states on each day, and we could say, you know, the weather on day 1 is x1, and it takes one of these 4 values, and then the weather on day 2 is x2, and so on, up to day n, say. And there's some probability of transitioning. So when if day 1 was a sunny day, there's some probability that day 2 will be a sunny day again. Maybe it's most likely, and maybe it'll be a rainy day, or maybe it'll be a cloudy day, or a snowy day. So there's some probability of transitioning between any 2 of these pairs. These are called transition probabilities. We'll talk more about that when we talk about the hidden Markov model. But even just in a simple Markov chain, you have these transition probabilities between any 2 states. So this would be a super simple discrete time, discrete space Markov chain. So now let's think about, you know, what are some, I mean, this seems a little bit maybe too simple. I mean, all of these things, you know, I mean, this one because there's not very many states, but there's a more fundamental problem with using a Markov chain. So there's a but. There's a big but. There's a few problems with this. The main problem is we can't expect, you know, we can't expect to perfectly observe the true state of the system, right? That was sort of what we were assuming. We were assuming that these x's are the state of the system as it evolves, and we were assuming that our data that we got were going to be maybe some subset of this. Maybe we don't get the last point, for example. We only get up to n-1 or n, and then we have to predict n+1. But it's unreasonable to expect that we would get that sort of perfect, true, you know, perfect information about the true state of the world or the system. So we can't expect to perfectly observe the true state of the system. For example, let's think back to these way back up here, to these sort of examples here. Well, let's think about this one. This is a good example. So with the GPS example, we had a robot, And the robot had some true position. It had some true latitude and longitude. Maybe it was doing something like this, is driving around. You know, maybe that's its true position, something like that. But what we observe, if we observed these GPS points up to time t, and we wanted to predict the position at time t plus 1, say, the true position, what we've observed was not, they were not perfect observations about the true state of the system. We had these noisy observations. They were noisy observations of the true state. And the same thing here with CO2. You know, maybe we expect that there's some, maybe that our measurements are sort of noisy because in a particular region or something like that, there's some variations. And maybe if there's some sort of true average, you know, some true total measure of CO2, that this is a noisy measurement of that. So back down here. So the problem is that this model is a little bit too limited because we're never going to observe the complete perfectly observe the complete true state of the system. So what's the solution? Well, one way to address this is to acknowledge the fact that there's some hidden information. There's some hidden information that we're not seeing. So there is hidden information. Or you could break up the state of the system into the observed part of the state and the hidden part of the state. And so you might say that there's a hidden state that you're not observing. And so under this sort of approach, we can model that hidden information with hidden variables or latent variables. Model with hidden or latent variables. And this is the approach taken in the hidden Markov model. And that's what we're going to look at next. So I'll stop here with this motivation for hidden Markov models. And it turns out that the hidden Markov models are actually, I mean, they are also sort of a simple in some sense, but they are general enough that hidden Markov models are extraordinarily useful. And in fact, the examples that I gave you earlier of actual implementations of Markov models are usually using hidden Markov models or some generalization of hidden Markov models.